An inequality relates two things that are not equal to each other. In example number 1, the left side is less than the right side. Now, in order to solve that inequality, we need to undo what's happening to n. Subtract 9 from both sides. And we're left with the opposite of n is less than 4. To solve, we need to get rid of this negative sign. To get rid of that negative sign, I'm going to multiply by -1. Now, negative times negative is positive, and negative times positive is negative. But there is a rule whenever we're working with inequalities. Whenever we divide or multiply by a negative, the sign must change. So we started with a less than. We're going to have to switch it to a greater than. So my final answer is n is greater than -4. The reason we have to switch this sign has to do with this statement right here. If the opposite of n is less than 4, then the opposite of n has to be positive n, and the opposite of 4 has to be -4, and the opposite of less than is greater than. So if we're going to switch all of these to their opposites, we have to switch our signs also. So my final answer is n is greater than -4. To graph my solution, I'm going to use a number line. And I'm going to put a point at -4. I'm going to put an open dot at -4. And -4 is not a solution to this inequality. So I can't include -4, so I'm going to use a open dot. Now I have a whole bunch of numbers that will satisfy this inequality. I'm looking for all the n values that are greater than -4. So I could pick numbers like 5, or 2, or 0, or -1, or -3, or -3.5, or -3.7, all the way up until -4, not including -4. So I want to include all of these numbers in my solution. To represent all of those numbers, I'm going to shade my number line. So this inequality actually has an infinite number of solutions. It's all the numbers that are greater than -4, not including -4. If I read this graph going to the left, I can get closer and closer and closer to -4, but not include -4. So I could include like -3.9, and then -3.99, and then -3.999, and I can keep getting closer to -4, but I can't include -4. And in this direction, I can pick any number all the way up to positive infinity. If I look at the original statement, if I plug any of these numbers into the original statement, I end up with a true statement. If I take 9 minus 5, I end up with 4, and 4 is less than 13. If I pick -1, 9 minus -1 is 9 plus 1, which is 10, and 10 is less than 13. So all of these numbers make my original statement true. Problem number 2 is a compound inequality. The reason it's a compound inequality is we're dealing with more than one inequality with the same variable. Both inequalities have x in them, but they're two different inequalities. To solve the inequality, to solve this compound inequality, I first need to solve for x in this inequality and then solve for x in this inequality. Now this problem is an OR compound inequality. This means that I have two choices for x. X can either be less than 0 or x can be greater than 17/4. To graph this compound inequality, I'm going to draw one number line and graph both of these inequalities on the same number line. I'm going to put an open dot at 0 and an open dot at 17/4. 17/4 is 4 1/4. So it's at 4 1/4. So my values for this inequality are 0 and 17/4. Now I have an OR inequality, which means that I can be either here or here with a solution. So x can be less than 0, which are the numbers to the left of the dot, or x can be greater than 17/4, which are the values to the right. If you look at this graph, I have some different choices for my solutions. I could pick -5, or I could pick +5. I could pick -1, or I could pick +7. What I can't pick are the numbers between these two values. If I pick a number between these two values, I do not satisfy one or the other of these compound inequalities. In order for x to be a solution for this compound inequality, I have to satisfy either this inequality or this inequality. If I look at the original, all of these solutions will make this inequality true, and all of these solutions will make this inequality true. Problem number 3 is also a compound inequality. Even though it only looks like one inequality, there's really two inequalities happening at the same time. This is a second kind of compound inequality. This compound inequality is an AND inequality, and this compound inequality was an OR compound inequality. In an AND inequality, I have to make both inequalities true. So I'm going to rewrite this compound inequality as two separate inequalities. So I'm going to start with what's in the middle here, 3t minus 8. And if I look, -2 has to be less than or equal to 3t minus 8. If I rewrite this and put 3t minus 8 on the left, 3t minus 8 has to be greater than negative 2. If you notice, this inequality opens up towards 3t minus 8. So I need to keep that when I rewrite my statement. And my other inequality is 3t minus 8 has to be less than or equal to 10. So this is how I get two inequalities out of this one compound inequality. Now I solve for t in both inequalities. Now this was a compound and inequality, which means that I need to satisfy both inequalities in order to have a solution to this total inequality. To graph my solutions, I'm going to use a number line. I'm going to put a dot at 2, but this time I'm going to put an open dot, or excuse me, a closed dot. I'm going to put a closed dot because of this or equal to symbol. That means that 2 can be a solution. Different than the first two examples where 0 wasn't a solution. I could get up to close to 0 but not include 0. I can include 2 as a solution to this inequality. The other place I want to put a dot is at 6, and I'm going to put a closed dot there because I want to include 6 as a possible solution. So if I look at all the values that are greater than 2, I would have all of these values to the right. Now if I look at all the values that are less than 6, I'd have all the values to the left. But this is a compound inequality, so I want the values that satisfy this inequality and this inequality. So the only values that satisfy both inequalities are where these two overlap. So it's going to be between these values. So I graph both inequalities on one number line, but this time I shade between the two values. If I look at my solutions, if I pick like the number 8, 8 is greater than 2, so it makes this inequality true, but it doesn't make this inequality true. So 8 is not a solution. If I look at 5, 5 makes both inequalities true. 5 is greater than or equal to 2, and it's less than or equal to 6. If I look at 2, 2 is also a solution to this compound inequality because it is greater than or equal to 2, and it's less than 6. But if I pick a value like 0, 0 is less than 6, but it's not greater than 2. So it makes this inequality true, but not this one. So 0 is not a solution because it only satisfies one inequality. Since this is an AND compound inequality, I can rewrite these two inequalities as one inequality. To do that, I want to find the smallest value between t, 2, and 6. Well, if you look, t has to be greater than 2, which means 2 is smaller than t. Now I want to find the biggest value. Well, t is smaller than 6, which means that 6 has to be bigger than t, which means that t has to be between 2 and 6. Now I need to put in the symbols. T is going to be less than or equal to 6. And if we look, T is greater than 2, which means that 2 is less than or equal to T. I can only rewrite compound inequalities as one inequality if that compound inequality is an AND inequality, because this means that T is between 2 and 6, and in this case with the less than or equal to including 2 and 6.